So using the calculator to crunch the number, 42,000 pound-feet divided by the square root of 13 feet gives us a force, force Z we've called it, of about 11,649 pounds. Now, the question is, what is the tension in member IH? Well, maybe we should redraw this triangle in a more standard position. So I'm going to redraw this triangle with this 11,649 pound force in the horizontal direction, and this hypotenuse that represents the tension at an angle, and the perpendicular to this this perpendicular vector I've drawn vertically. This angle here, 22.6 degrees. And if you think about the tension in IH is the hypotenuse, right? So I'm trying to relate the side of a triangle that I know and the hypotenuse, right? So it's this is kind of, we could label this side hypotenuse. This side would be opposite the 22-degree angle. This side would be adjacent to the 22-degree angle. So I think about what function relates adjacent and hypotenuse. Well, it's the cosine. So let's write the formula. So cosine of 22.6 degrees equals what? Adjacent over hypotenuse. So 11,649 pounds divided by the length of the hypotenuse. Now, I'm trying to get the hypotenuse by itself. So what do? I multiply both sides by the hypotenuse. On the right side, they cancel, and I get the hypotenuse times the cosine of 22.6 degrees equals 11,649 pounds. But my general strategy is to get the variable alone, so I'm going to divide both sides by this cosine of 22.6 degrees. On the left side, it goes away. On the right side, I'm left with this force divided by this cosine. So if I use the calculator, I'm actually going to start by finding the cosine, and this is just kind of a product of how the calculator handles numbers. So cosine 22.6, and I'm going to get that number. Actually, on this calculator, you got to say 22.6, drop it in the cosine machine. There's the cosine of 22.6 degrees. Then I'm going to, actually, let's just add this to the memory. So now we'll clear out of here, and I'll say 11,649 pounds divided by, recall what's in the memory, which is that. And I find that the tension in member IH is about 12,620 pounds, give or take. So the tension here, this tension in IH, 12,620 pounds. Now let's see what else the problem asks us to find. So the next thing we're asked to find is the force and component HC. And I can come up with this because of some of the things that I've already figured out. I know that this included angle in here is 56.3 degrees. And I know that the tension in this is about 12,620 pounds. And actually, without rounding, it's about 12,650. So I could redraw this triangle over here that has this hypotenuse of 12,650, has this included angle of 56.3 degrees. And I want to know if the tension is pulling in this direction, I want to know what the leftward force is. So I'm going to call this the adjacent side. I need to relate the adjacent side, the hypotenuse, and the angle. And again, the function we're going to use for that is cosine. So I say cosine 56.3 degrees equals what? Adjacent over hypotenuse. So A over 12,650 pounds. How do I get A by itself? I multiply both sides by 12,650 pounds. So 12,650 times the cosine of 56.3 degrees is going to equal A. So again, using the calculator, I'll take 56.3, take the cosine of it, multiply that by 12,650. Oops. And I find that the force is 7,000, call it 7,000 pounds. So what does that mean? Well, it means that the leftward thrust that is created by member HI, you can think about member HI pulling point I to the left with 7,000 pounds thrust. Now, I'm going to solve this by method of sections. And so what I'm going to do is I'm going to section this truss right here. And I'm going to think, and I'll cut it here too, and I'm going to think about static equilibrium. So let's think about the sum of the forces in the x direction. Well, I've got 4,000 to the right plus 6,000 to the right here, plus this negative 7,000, this 7,000 pound leftward pull that the tension in member HI is causing, plus some force in the x direction in member HC. And if this is going to be in static equilibrium, they've all got to add to 0. So I look at this and I say I've got 10,000 positive, 7,000 negative. I say that I have 3,000 plus the force in the x direction in member HC equals 0, or the force in the x direction in member HC equals negative 3,000 pounds. So what does that mean? That means that member HC is pulling point C to the left with 3,000 pounds, or the fact that this is under tension. So we'd say tension of HC equals 3,000 pounds. Let's see what else we're asked to solve for. The last thing you're asked to solve for is the force in member CD. So let's take a look at CD. That's right here. The way I'm going to solve this is by method of joints. So I'm going to place a pivot at point H. And I'm going to start with thinking about the sum of the moments about point H. So if I look at the sum of the moments, well, I've got this 6,000 pound force acting on a lever arm that's 3 feet long. So 18,000 pound-feet plus, and I want to think about kind of sign convention. That 6,000 pound force is going to make this want to rotate clockwise about point H, and we consider a clockwise rotation to be a negative rotation. So I'm going to put a minus sign in front of that moment. What else do I have? I have a 4,000 pound force acting on a lever arm that's 6 feet long. So, and again, that's going to produce a clockwise rotation, so negative 24,000 pound-feet. And then the last thing that I have as I look at this structure is I have this member CD, and if I think about kind of the moments I've created so far, they're both clockwise. Member CD must be generating a counterclockwise moment about point H, which tells me, first of all, that member CD's got to be in compression because it's got to be pushing up. And specifically, it's going to be the plus the force in the y direction at point C times the length of the lever arm here, which is 4 feet. And again, those all need to add to 0 because we're in static equilibrium. So if I rewrite this a little bit, I'm going to get the force in the y direction at point C equals, I'm going to push the 18 and the 24 over to the right side, which is 42,000. Now it's a positive 42,000 pound-feet, divided by the length of the lever arm, which is 4 feet. So notice that this works out because we're dividing feet by feet. Those units cancel. I get 42,000 divided by 4, which is 10,500 pounds. And again, we've already determined that this is in compression. So, through that analysis, it took some jumping through hoops, but there was really no new math in here. We've been able to determine the forces in CD and HC and HI. And this is the type of thing where we could use that knowledge to, for instance, determine which of those would fail first under fire conditions.